all, the standard for this video is transformations of functions. We're going to start with an equation and make the graph, and then work the other direction as well. We'll start with the graph and make the equation, or maybe just a description of the transformations. We can get an equation from that as well. Most of the toolkit functions you had, we just wanted you to kind of learn the shapes so far, and now we're going to move them around. Since most of them are centered around 0, 0, we're going to focus on those points and use this locator point method. Some of the other graphs where we have to do a little bit more work we'll do when we actually graph those later in the course. But all the transformations will work about the same way. So we're going to break it down step by step, and then we'll do some together, which I think makes more sense, but we'll start here just so we can kind of see what's happening. So graphs of the form f of x plus k are first. A function of the type f of x plus k represents a vertical shift of the graph of f of x. If k is greater than 0, we go up k units. If k is less than 0, we go down k units. So this locator point, you may have heard of a vertex before for your quadratic functions. Like I said, most of those toolkit functions are kind of centered around the origin. And that 0, 0, when we do work into the stretching and compressing, or when we're multiplying or dividing by values, that 0, 0 is not going to change. So we can just kind of follow it around with our shifts up and down and left and right and call it a locator point. And then we'll worry about the shifting or the stretching and compression from there. So just start with this locator point at 0, 0. If we are shifting the graph up 3 units, our new locator point is going to be at 0, 3. The other thing we want to look at is these slope triangles, and we can kind of follow these to see how the graph moves. So for the original function, I'm up 1 over 1 to get to my first point, and then I'm up 4 over 2 to get to my second point. So we can go a 1, 1 here, and a 4, 2 up here. And we can use that to help us transform the rest of the points after we found the locator point. And we'll do more with the triangles when we actually do those stretching or compressing later on, or those when we bring in the factors. But for this graph, we can just move everything up 3 units. So 3, 4, 5, 6. I got to go up to 7, right, for my points that were at 4. But my locator point starts up there at 0, 3 on the y-axis, and then I'm still going up 1 over 1 to get to my first point to the right, up 1, left 1 to get to my first point on the left, if I'm following those around, and then up 4 over 2 to get to my point. 2 out to the right, and up 4, left 2 to get to my point on the left. All right, but easy when there's only one movement. We can see we really just shifted every single point up 3 units. All right, for x squared minus 3, h of x here in c, we're going down 3 units. So my new locator point, what I'm going to open around, is 0, negative 3. So I can take that same original graph. I'm going to go down 3 units for my new starting point, or locator point. And we're still going to use that same triangle, up 1 over 1, and then up 4 over 2. So up 1 over 1, up 1, 2, 3, 4 over 2. And we can do the same thing out to the left to keep the shape of that graph the same. For graphs of the form f of x minus h, a function of the type f of x minus h represents a horizontal shift of the graph of f of x. So we really want to focus on the difference of being inside or outside that base function. So inside the squaring, or inside the absolute value here, underneath or outside the square root. Everything inside is going to affect x, everything outside is going to affect y. And that's why the plus 3 or minus 3 we had after the squaring function changed our y value, it shifted us up or down. The value inside here is going to act on whatever we substitute in for x before we take the absolute value of it. So it's affecting the x value before we get the actual function value. So for these ones, everything inside is going to look opposite of what actually happens. So we have here, if h is greater than 0, the graph is going to shift to the right. And so we see that for the first one, this x minus 2, our h is greater than 0. H here is just 2. so it's going to shift 2 to the right. And if h is less than 0, the graph is going to shift h units or absolute h units to the left. So really h here is -2, and that's when we get that x minus -2 becomes the x plus 2 we see inside, but that's going to shift us 2 units to the left. And for our locator point, for our absolute value function, we start again with that origin 0, 0. If we're shifting 2 to the right, our new locator point here for B becomes 2, 0. And our new locator point for C is going to become a -2, 0. Right? We didn't shift anywhere up or down this time, just that left-right movement inside. I can see from my graph, my original, I'm still going up 1 over 1, or up 2 over 2 to get to my next points, or up 1, left 1, up 1, left 2, right? Those triangles. So we can do the same thing with our locator point here. We're going to start at 2, 0. So I've just shifted to the right. And then we're going to do the same thing with those triangles. We're going to go up 1 over 1 to the right, up 1 over 1 to the left, up 2 over 2 to the right, and up 2 over 2 to the left to get our whole graph. And we just want to sketch. We want you to know the shape. So my scale is not going to be perfect. Yours might not be perfect. But we do want to see that you recognize absolute value and where that graph is supposed to live. For this one, my locator point took me 2 to the left. So -2, 0. And then our slope triangles still take us up 1 over 1, up 1, left 1, up 2 over 2, and then up 2, left 2 to give me my graph shifted left. And you can see at this point, with just one transformation at a time, it should look exactly like that original or base function, just every point is shifted 2 points to the left, or 2 points to the right for B. For graphs of the form minus f of x and f of minus x, we're working with reflections. If we multiply outside, so a function of the type minus f of x, we reflect over the x-axis. It's maybe opposite of how you read it, but it's changing all the y values, right? If we're multiplying outside, and if a positive y becomes negative, we've reflected or moved over that x-axis. Alternatively, if the minus is inside, it's affecting all the x values. So it's happening on x before we take the function value or take the absolute value, or before we square, before we take the square root. So it's changing all the x values. So it's going to flip over the y-axis. So don't need to do a whole lot with the locator points here. We haven't shifted it all left to right or up or down, so maybe we can just talk about the values. So the negative outside here affects the y, or the function value. So we're going to reflect over, that's not an over, reflects over the x-axis. So our graph is going to look exactly the same, but come down here over the x-axis. So instead of being up 1 over 1, I'm going to go down 1 over 1. Instead of going up 2 over 4, I'm going to go down 2 over 4. And I'll get that graph coming down into quadrant 4. Right, and we can see reflected right over that x-axis. So all the x values stayed the same, 1, 0, 1, 2. 4, but the y values are now negated. Instead of 0, 1, 2 on our points, we're 0, minus 1, minus 2. The negative inside affects x. So we're going to reflect over the y-axis. So we can start thinking with that same parent graph, but now we're going to go out to the left here. That 0, 0 stayed in the same spot. Instead of going up 1, right 1, I'm going to go up 1, left 1. And then I'm going to go up 2, left 4. So I can see that whole graph has been moved over the y-axis. And this is how we're able to get some negatives underneath the square root. If I substitute in -1, I have minus, or the opposite of -1, which becomes 1. The square root of that is 1. So I get my point at -1, 1. If I substitute in -4, the opposite of that is 4. Its square root is 2. So I can see that shift over, or that flip over the y-axis, right? I can only sub in the negative x values now. All right, we can also do some multiplication. For graphs of the form c f of x and f of cx, where c is a positive real number, we're bringing in these factors now. We're either multiplying outside or inside that base function. The functions of the type c times f of x, where we're outside that main function, are a vertical stretch or compression of the original graph. We're multiplying the y values by something, so it's going to pull our graph up, or squish it in if we're multiplying by a fraction. A function of the type f of cx represents a horizontal stretch or compression of the graph of f of x. We're multiplying inside affecting the x, so it's stretching or compressing in that x or horizontal direction. For these ones, we're not shifting at all, so we can note that the locator point is still 0, 0. But we're not going to affect it at all, because multiplying or dividing 0 by something is not going to change anything. But we will affect those slope triangles now. So we were up 1 over 1 and up 2 over 2. So we can think about those triangles to get to our other base points for the parent function. And we can talk about how those values change, whether we're multiplying inside or outside. So for g of x, the 2 is outside the function, so it's going to affect y. So for our slope triangles, we're going to multiply the up and down, or y movement, by 2. Right? So that triangle has become a 2, 1. We're going to go up 2 over 1 to get to our point. And for our triangle that was 2, 2, when we multiply by 2 for that y movement, that up-down movement, we're now going to go up 4 over 2 to get to our second point there. And we can do the same thing left and right for this one. Right? Still want it to look like that absolute value function. So we're still at 0, 0. We're going to go up 2 over 1 to get to our first point, and then up 4 over 2 to get to our second. We'll go up to left 1 to move left, and up 4, left 2 to get the last of those kind of 5 base points out there we have on the original graph. All right, so you can see it's stretched up, right, a little bit taller than it was before. And for h of x, c here, where the 2 is inside, we're now affecting the x. I don't remember exactly what I said up top, but anything inside is treated kind of opposite of what you see. The thought is when we plug in something for x, it's going to get multiplied by 2. So we want to divide to figure out the values to kind of sub in. So when we take our slope triangle, we had a 1, 1, and we had a 2, 2 for the absolute value. And we could do the negative going the other direction, but we can see hopefully they're the same here. We are going to actually divide the x values by 2 to get our new triangles. So we're going to have an up 1 over a half, and then we're going to have an up 2 over 1. And you can see maybe those ratios are kind of the same as the ones we created to the left. We're just affecting the x instead of the y. And you'll see in a minute the graphs are going to look very, very similar. We just have to worry about half steps now. I'll still go by 1s everywhere, even though I haven't labeled them all. But our locator point still at 0, 0. We have no shifts left or right. Instead of going up 1 over 1, we're up 1 over a half and up 2 over 1. We can do the same thing going to the left, up 1, half to the left, and up 2, whole to the left. And so it looks, hopefully, very similar to your graph for b that we just did. You can think maybe if we do move out another 2 or another 1 unit, we're going to go up another 2, right? Another 2 and 1 to kind of follow that slope triangle up. And that works for the absolute value because it's made of these linear pieces. But The idea is this is a horizontal compress, right? Since we were less than 2, a fraction is going to stretch it out. But you can see it's kind of doing the same thing. So it just depends on what you're talking about, if it's the y or the x value. But it's doing kind of the same thing to the graph. We'll do some, hopefully more now together with lots of movements that'll make some sense. So now we're going to graph using those transformations. For 5, we've got 2 functions, maybe 3 here. But for a, we've got f of x equals x minus 1 cubed plus 2. So we're working with our cubic function. If it helps you to know, hey, this is our parent graph. That's what we wanted to get from the toolkit functions. Our locator point for that parent graph was still 0, 0, right? It runs right through the origin. That was our x and y intercept for that graph. Our locator point for our transformation, you can say for f of x, if it helps you keep it straight, we are going 1 to the right and then 2 up. So our new locator point is at 1, 2, or that's our h and our k. All right. We have no multiplication, no factors outside or inside, so that's our only shift. So we want to do the same thing with our points. I will draw the base graph out here just so we can see it for this one, and then we can draw the nice graph on the one provided there. Sometimes we only follow 3 points, so we didn't have enough listed on here. It's a smaller graph, but we'll make it work. So our original graph was 0, 0. If we cube 1, we get 1. If we cube 2, we get 8. Those are the points that were hopefully listed on that toolkit function when you got it in the other notes. If we cube -1, we get -1. If we cube -2, we get -8. So this is the function we're going to move around. And we want this one so we can see those slope triangles. We won't need a lot for this one, but we will for the next one. So up 1 over 1, and we were up 8 over 2 to get to our points. And then we could go down 1, left 1, and down 8, left 2. So if we go to our new locator point on the graph over here, I'm just going to go by 1s everywhere so I don't write a bunch of numbers. But we'll go over 1 and up 2 to get to our new locator point. And then with these triangles, we're up 1 over 1, down 1, left 1, and then we've got to go up 8. So that's where we go off the graph here. 1, 2, 3, 4, 5, 6, 7, 8. It's not going to be perfect, but it's way up there. And we can go definitely down 8, left 2. That's easier. 1, 2, 3, 4, 5, 6, 7, 8, and left 2. Whoops, we want to go always from that locator point. So we're 2 down and then 6 more. Take us to here, left 2, right there. All right, and then we can draw our graph through that point. So we just want to sketch. All we did was shift everything 1 to the right and 2 up. And we can see that locator point in black, still the one we're always going to go back to when we're using our triangles to draw the other points. All right, for B, we have some movements. If you don't remember the parent function for this one, it is 1 over x. Our locator point is not a point, but it's still going to be 0, 0. If you remember what 1 over x looks like, I'll put the parent graph here so we can do our work in a sec on the main one. The parent graph is the one that goes down here in quadrant 3 and up here in quadrant 1. And it goes through the points 1, 1. And -1, -1. So we can kind of follow those around as we go. And then it's shaped by what are called, I don't think we've done them yet in this class, asymptotes. So we'd have a vertical asymptote going up and down the y-axis and a horizontal asymptote going along the x-axis. And the function's just going to run along those asymptotes. That's going to guide the graph for us. So really we're shifting those around by shifting that locator point. So for our new function, for g of x, our locator point is -3, -4, right? We have that x minus h down here under the function. So if it's x minus something, it's minus a negative 3. And then we can see the minus 4 outside for our shift down. So left 3, and then down 4. We also have a minus 2 that we've multiplied by, and so we're going to use that one with the slope triangles for this. So if 0, 0 is our locator point for the original, we're going up 1 over 1 to get to that point we can follow, that 1, 1, and down 1, left 1 to get to the minus 1, minus 1. So we'd have a slope triangle that looks like this, 1, 1, and we can do the one going down just to transform both. That's a minus 1, minus 1, right? We went down and then left. If we're multiplying by negative 2, I'll keep this weird yellow color, we are changing the y values by negative 2. So my new slope triangle becomes a negative 2, 1. And the one for going down becomes a 2, right? Positive now, and then 1 to the left still. Negative 1 there. All right, so we can use those to track some points. We can plot our point at negative 3, negative 4, that locator point. And we can dash in those asymptotes if it helps you graph. We'll do way more with asymptotes later when we do the rational functions. For now, we just have them for this 1 over x function. And then we can find our nice points from there. We're going to go down 2, right 1, and we're going to go up 2, left 1. Right, we'll follow those slope triangles. And then we can draw in our graph through those points along our curves, right, along those asymptotes. And we can see that reflection of the original graph right over the x-axis with the negative there. For 1 in general, for C here, we have y equals 3 times h of x plus 2 minus 5, where h of x is the graph shown below. For these ones, we don't have that 0, 0 that's not affected by the factors, by the multiplication or division. So really, we just want to think about what's happening to each point. And this is where we can really talk about the shift or the stretch and really what's happening to the x's and the y's. So I'm going to make a table of x, y values, and we're just going to affect each one as we can see in the equation there. So we start with a point at 1, 2, and then 2, 2, 3, 2, 4, 3, 5, 2, and 6, 0. From the graph, we can see that we are going 2 to the left, right? The plus 2 inside would be an x minus negative 2. We are going 5 down, and we've got a multiple of 3 outside, so we're multiplying y by 3. Right? It's outside the function, so it affects the y's. Multiply y by 3. And so we're going to do that to all the values in our table. If we did have a shift inside, which you won't see too often for these types of functions, we need to remember that everything inside is backwards. So even that order of operations would be backwards. And maybe we'll do one hopefully together in class so you can see it. But for all the x's, to shift them to the left 2, we're just going to subtract 2 from all of those values. For the y's, we are going to multiply by 3 and then go 5 down. So for the y's, we just use order of operations. Everything happens as it would when we substitute in our values. So for x, we want a minus 2, all the way down. That's going to give us some new points. I guess I didn't leave good room there. Let's move the middle. That's easier. So we're going to get new points. X coordinates negative 1, 0, 1, 2, 3, and 4. And for the y values, we want to multiply by 3 and then subtract 5. Right? Every single point is going to be stretched and then shifted down. So we'll get some new y coordinates of 1, 1, 1. There we get a 9 minus 5, 4. 6 minus 5 back to 1. And 0 minus 5, a negative 5. And we can plot those new points on our graph. So we've got a point now at negative 1, 1. 0, 1. 1, 1. 2, 4. 3, 1. And 6, negative 5. And it'll keep the same shape as that graph. So we had that kind of constant piece, a little parabolic piece, and then a linear piece dropping down. All right, we finished with a couple going the other direction. For 6, we're going to write the equation for the function graphed below. We can see or identify our locator point from the graph, as long as we recognize the type of function. This is quadratic, or that squaring function. Our new locator point, instead of at 0, 0, is over at negative 2, 0. And we can use a slope triangle to think about how we've changed. So we know for our base function, we would have gone up 1 over 1, and then up 4 over 2. Right, so we would have had a 1, 1 triangle, and then a 4, 2 triangle to get to those two normal points. You can see the reflection, and you might just throw that in by yourself here. We also want to take note of the fact that we are over 1 to go down 3, or really down 3 to go over 1. So we've got a negative 3 and a 1. Right, that negative 3 over 1 tells us that we're multiplying by a factor of negative 3. Right, we've stretched that triangle out, and we've shifted it down. So now we're at a negative 3, 1 instead of a 1, 1. And so we can kind of think backwards of what we did before. And so our new graph here, we're going to use a y equals negative 3 outside. Our locator point's got that minus 2 in there. That's our h. So x minus h, or x minus negative 2 squared. And there's no plus or minus. We didn't shift up or down. So if we simplify inside there, we've got a negative 3 times quantity x plus 2 squared. We can see that slope triangle affecting that factor right out front. For b, we've got an absolute value function. Our locator point for that one would have been 0, 0 originally. We can see now it's at negative 3, negative 1, so we've shifted left and down. For the factor, we can look at the slope triangle again. We would have been 1, 1 on the original function. Here we can see we're going up 1 over 3. And we could put something inside, or we can just think back to the ratios with those similar triangles. If I divide both of those by 3, I'd have a 1/3 and a 1. So I've kind of moved my shift to that y value, and we're going to multiply by a 1/3. So we have a y equals a 1/3 absolute value of x minus negative 3 minus 1, or a y equals, don't need to rewrite it, but a 1/3 absolute x plus 3 minus 1. Last one, just with the equation here, we're going to write the equation for a function that has a shape of f of x equals square root of x, but has been shifted 2 units left, 4 units down, and reflected over the x-axis. Just so we can get used to the words a little bit, 2 units left means our h is minus 2. Right, 4 units down gives us a minus 4 for our k. You don't have to write the h's and k's, but just to get used to it. And this reflect over the x-axis means we're affecting the y's, so we're going to multiply a negative 1 out front. We put those 3 things together and we get a, maybe now we call it f of x, let's call it y or g of x. But y would equal a minus square root of x plus 2 minus 4. Right, that left 2, we want that plus 2 inside, so we can see that negative h, and then the minus 4 for our shift down outside, multiplying by that negative 1 in front to affect the y's and flip us over the x-axis. That's it for the notes. Try the ticket. See you in class.